All right. Hello, everyone, and welcome to today's cryoEM Current Practices webinar. You're joining the three NIH-funded National Cryo-Electron Microscopy Centers. My name is Christina Zamani. I'm a scientist and training liaison at the National Center for cryoEM Access and Training, NCCAT. Also with us today are staff members from each of the centers, including my colleague here at NCCAT, Ed Eng. From the Pacific Northwest cryoEM Center, PNCC, is Kirsten Wheeler. And from the Stanford SLAC cryoEM Center, S2C2, are Nathan Burrows and Michael Schmid. For our main event today, S2C2 has invited our speaker, Mark Herzik, who's joining us from UC San Diego. But before we give the floor to our speaker, we'll have a quick update from each center on the resources we make available at no cost to the research community. And then Nathan will properly introduce our guest. This webinar is a regular event we host the last Thursday of each month, highlighting users of the National cryoEM Centers who are kind enough to share the tips and tricks that have enabled them to make use of cryoEM in their research. You can save the date for our talk on July 30th. We're starting a short streak of University of California highlights, and Professor Jennifer Cash from UC Davis will give a talk in July titled cryoEM Single Particle Analysis of Small and Dynamic Proteins. If you want to join us for that, you can already find the registration link on the events page at cryoemcenters.org, where you'll always find registration for upcoming talks and recordings of our previous talks. I also wanted to highlight that our August webinar will be a special event with a panel of former users and trainees who now work across the larger cryoEM ecosystem, who will be sharing career tips and tricks rather than sample tips and tricks. And the registration is already on the cryoemcenters.org site for that session. For final logistics today, if you have questions about accessing National Center resources, please feel free to reach out directly to any of the panelists at any point. But for questions for our speaker, please use the Q&A box to send them in. Michael will be fielding those. We may take some of them as the talk goes, but anything we don't get to, we'll hold for a moderated Q&A at the end. So let's go ahead and get started. So first, I will ask Ed to let us know what's new at NCCAT.
Hi, at NCCAT, we have quarterly calls for proposals. Our next deadline is July 1st for data collection, grid prep screening, and training. I know we were talking about summer conference season last month, but I want to point out the 11th International Congress on Electron Tomography is August 9th through 12th in Madison, Wisconsin. Deadlines for registration is this coming Tuesday on June 30th, so don't forget to apply. And then if you missed the first annual Western New York Structural Biology Collaborative meeting in Buffalo last year, this year is going to be University of Rochester on July 28th. So hope to see you in your neck of the woods soon. If you want to find out more, please go to ncat.nysbc.org.
Thank you, Ed. Next, I'll turn over to Kirsten.
Hey, good morning. My name is Kirsten Wheeler, and I'm the program administrator at the Pacific Northwest Center for cryoEM. That's in Portland, Oregon. We have two types of proposals we offer for our resources access. And the first being a screening access, which allows one person to come on site for up to 5 days of sample preparation and screening with staff. The proposal is aimed at low resource institutions needing preliminary data. The second type of proposal is our general access, which awards up to 480. Ooh, sorry, spam callers, right on time. It awards up to 480 hours of microscope time a year for 2 years. The time can be used for screening or data collection. Approved general access proposals are also eligible to apply for our training programs. We offer a variety of workshops that cover the entire cryoEM pipeline. That would be grid preparation, screening, data collection, data processing, and many more. Our next upcoming workshops, we actually have our first iteration for a hands-on modeling workshop that's taking place in September, with the sample preparation workshop in October that's also hands-on. Current users are welcome to apply with applications currently open. All approved proposals are assigned a PNCC staff member known as a scientific point of contact. SPOC is what we end up calling them. They can help you with questions about sample optimization, data collection strategies, and so on, as well as the fact that we have six microscopes that we utilize: Antarctica, Glacios 2, and 4 Krios. In addition to that, we have multiple pieces of equipment for sample preparation. If you're interested in working with us, please go to pncc.labworks.org and apply. Our deadline for proposal submissions is the first of every month. We look forward to working with you.
Thank you, Kirsten.
Yeah.
Next, I'll let Nathan let us know what's new at S2C2.
We're keeping busy at S2C2 as well this summer. We just have finished accepting applications for a sample prep workshop this summer. We're planning a data processing workshop. We have our two main scientific access programs for high-res data collection and a screening grid optimization program, as well as our training program as well, with application deadlines at the first of every month. And that's pretty much what we have going on here. We're also blessed with the suite of equipment that most of the national centers have here. With that, I'd like to introduce our speaker for today. Our speaker is Dr. Mark Herzik, who's an assistant professor at the Department of Chemistry and Biochemistry at the University of California in San Diego. His lab is really interested in the underpinnings of molecular transport within eukaryotic cells specifically. And today he's going to be sharing us with some of the tips and tricks that he has developed in his lab in pursuit of these goals using cryoEM, particularly dealing with dynamic, oxygen-sensitive, and air-water interface-prone systems. So I think everyone will enjoy learning from Mark and sharing his experience today.
Thank you so much. So thank you for the introduction. I'm happy to say that my group has now used all three of the national centers and had great success. So I applaud both their services and their capabilities. I'm also happy to say that as of July 1st of this year, I get to grow from assistant to associate. So this is one of my first talks on this platform. So thank you very much. Okay, so what I'm gonna do real quick is talk about kind of where my lab is focusing a lot of efforts right now. And so I think everyone, for the most part, is familiar with the basic cryo-EM workflow, especially for single particle, where we go from sample prep to grid prep, data collection, and then data processing. And I think one of the things that I have found most interesting is over my tenure in the field, the basic breakdown of how much time we spend has kind of been inverted, where when I started a little over 10 years ago, data collection, data processing basically absorbed an insurmountable amount of our time. And now with the high-end instrumentation, better workflows, faster workflows, and automated modeling programs, it's basically been an inversion to where now sample preparation and grid prep absorb a large amount of our time. And then even once we get what we think are good grids or good samples, we spend a lot of time going back and forth with feedback from either data collection or even data processing to inform on how well our grid prep did or how poorly our sample behaved and how we can improve things. And I would also say that for a lot of samples, we still spend a large amount here because the microscopes are so fast and really robust for what we typically need. And so in my group, we like to think of this problem as kind of the three interfaces that define success. The first one is what we define as the chemical environmental interface, and this is where we spend a lot of our time on the sample before we even vitrify it. All right, so optimizing buffers, constructs, complexes, you name it, because let's be honest, once we put these things into an EM grid and smack it with blotting paper, all things are more or less off. Now, once we start to vitrify our sample, we then have the air-water interface, we have air-surface interfaces, we also have a lot of kinetic interfaces during the freezing process as a result of shear stress, capillary action, all kinds of different things. And so my group has also focused many different manuscripts on how we approach these. And then the algorithmic interface is unfortunately one of the most subjective aspects, I think, of cryo-EM, where you can take a great sample, a great data set, use the wrong parameters, and have a poor outcome. Or you can actually work with the latest and greatest algorithms and get all kinds of different data. And so A lot of time we also spend at the algorithmic interface optimizing how do we deal with heterogeneity, how do we deal with dynamics, and in this case, what I'll talk about today, preferred orientation. And so let's focus a lot of this talk on how my group has approached dealing with the air-water interface. And so when I was in my postdoc, I was a big advocate of the manually operated plunger. And for those who have not experienced this, you take an EM grid that you've made hydrophilic with a plasma or something like that, apply your sample directly to the surface, and then you smack it with blotting paper, just like what you would see here. And this little 3 millimeter EM grid carries your sample for perpetuity. Now, during this process of smacking with the blotting paper, you can see how much liquid is removed from the surface of the grid. And unfortunately, during this process, which is usually about, 8 to 10 seconds or so, you have shear stress, you have capillary action, you have airy fingers, which I think is a term that Bob Glazer and his group coined. But then also you have other effects from the blotting paper itself. You have calcium and other small molecules, phosphates, metal ions being dumped into the sample. And so during this, 8 to 10 seconds, your sample is encountering a lot of different physical chemical things that can affect the downstream outcome. And so then once you vitrify the sample, you can then store it in a grid box almost indefinitely. You can send it to the cryo-EM centers. And if you're really lucky, you can get an atlas that looks like this, where you have lots of real estate to collect, for a perpetuity. And so this is actually a grid that I froze in my postdoc that we used for benchmarking for I think 2 or 3 years, where we just kept putting it in and out. Now, the downside to this, though, is when you get a grid like this, you have kind of buyer's remorse in some case, where you'll collect here, you may get good images, you may not. Then you'll move to here, then you'll move to here, then you'll move to here, and you'll end up sometimes spending 30, 45, 60 minutes on the same grid trying to find the best real estate. And so one of the things that we thought about is, well, in a single EM grid, you can have an ideal situation, right? You can have non-absorbed particles, no preferred orientation, where your very happy sample is freely floating dynamically in solution. You flash freeze it, you vitrify it, and then you recover pretty much all these different orientations. Now, in some cases, right, you can have a particle at the air-water interface. It sticks there, but it doesn't have a preferred orientation. You still recover a lot of the views. This is still a somewhat ideal scenario. You can deal with this because you still have multiple views. Or in some cases, it'll be at the air-water interface. You don't have denaturation or sample integrity loss, but you still have in preferred orientations. And as long as in honestly is more than 3 or 4, in most cases, you can still process the data and recover a good 3D reconstruction. And then down here in red is pretty much the worst case scenario, where you'll have particles at the air-water interface. They're stuck there. You then have partial denaturation, which could either be a subdomain that's unfolded as a result of shear stress or the changes in the hydrophobic nature of the air-water interface. And you typically have limited preferred views here. It could be 1, 2, or something worse than that. And then also a lot of times coincident with this, then you'll have particles that can completely denature. And let's be fair, pretty much all of these can be encountered both within the same hole or even within the same grid square or grid itself. And so a lot of screening ends up happening here. And the outcome of these worst case scenarios is that you have a sample here where the silhouette is shown with this gray outline. This is a hemagglutinin trimer. And then as a result of preferred orientation, limited view sampling, you don't recover the full density. And so when you have this situation, you can't build an atomic model, you get no biological insights, everything is pretty much lost because the sample cannot be recovered. And so what's interesting is we've been dealing with the air-water interface pretty much since the dawn of time, right? Since before EM grids were even made, we started to worry about the air-water interface issues and how to deal with it. And you can see here the number of publications associated with this has not died off effectively. We have not solved this problem no matter how good we become. And I think part of this is because when you first screen your samples, you're looking for something like this, where you have here is the film or the foil of your EM grid. Here are your particles. You have great particle density. They're nice and homogeneously distributed. And then you look at a cross section, you can see here they're not stuck to the air-water interface. This is an absolute ideal situation. Now, we don't always encounter this, and sometimes we'll get a situation like this where these same particles tend to cluster at the outer rim of the hole, where the ice tends to be a little bit thicker. But if you still have the views that you need and they're not overlapping, you can still collect data and reconstruct your particle. Now, suboptimal then gets worse as you start to have them basically decorate the edge of the foil or even on top, nothing in the center. And then absolute worst case is when they're in the center, but unfortunately they're preferred and you can't recover views even through different approaches. So now the bigger problem here is that many specimens do appear very well behaved on the grid. They may look like this with good, nice density, but because of air-water interface interactions, you then start to process your data and realize during 2D classification or 3D reconstruction that, in fact, this particle density was a result of particles adopting pretty much the same view. And so then the question becomes, well, do we prepare different grids? Do we change the sample? Do we look at different ways to recover the viewing distribution through algorithm, or what do we need to do? And so one of the ways to approach this can basically be binned into three different modalities. First and foremost is solid support films or grid modifications, where basically you can add a surface. And so what you do is you take your grid and you replace the surface with some sort of grid support. This can be graphene, graphene oxide, or even amorphous carbon. And so you replace one air-water interface with an air surface interface. What's great about this is they can be functionalized. You can add different moieties that can use for affinity capture. You can pegylate. You can do all kinds of different stuff. They're a lot of times cheap and really easy to make, and they can be typically stored long term. The caveat here is if you store them in a plastic grid box or a plastic box for long term, the off-gassing of the plastic will actually stick to the surface that you've now functionalized, and it'll ruin the chemistry effectively. Now, previously, the cons associated with this, especially for amorphous carbon, was that they're not great for small samples. You're scattering through something, you decrease your signal to noise ratio. And so, a lot of times, if you had a small, and I say small, less than 200 kilodalton sample, and you had preferred orientation, amorphous carbon was more or less off the table. Now, with graphene technology, that's no longer the case, and it works great. The other downside with these is that they tend to be fragile. And so as a result of this, during grid handling, actually blotting them with physical blot paper, they can crack, be damaged. You'll get microfractures that you won't see until you actually image them. With instrumentation, we have two ways to kind of approach this issue. One is they can do tilting, which the Lumpkins group was a pioneer for, where you can basically just take the same specimen with your in preferred views, physically tilt it within the microscope, and then you get kind of a cone of different views. This works great, but it does increase the scattering thickness of your specimen, decreasing signal to noise, and it won't prevent the fact that if your particle has been denatured or damaged at the air-water interface, you're going to be averaging a damaged specimen. Then the chameleon or the spotted on instrument came into play, and this was sold as more or less a silver bullet for fixing air-water interface issues. That may not be the case because it does change the physical chemical properties of the air-water interface, but it doesn't completely eliminate it. And the benefit with these two is you can basically tune the ice thickness, right? You can dictate how much tilting you need to do, how much ice thickness you can tolerate for your specimen. And then with the chameleon, you can tune how much blotting time you have based on the actual wicking parameters. Now, the downside to this is that this costs a lot of money. It's not a silver bullet. And then this here works great for most microscopes, but because you increase the SNR, sometimes it doesn't really work. And then, of course, the addition of small molecules and surfactants has been by far the most common across the ages. They're cheap and really easy to add. The other benefit is they can be stored long term in stock solutions, and so you can add it pretty much agnostically to any sample. and there's a proven track record. A lot of the air-water interface documentation that we've come across uses small molecules to help flip views. Now, the downsides of this is again, anything that's less than 200 kilodaltons, you need ideal SNR. And so when you add something into the solution that's going to scatter, like most surfactants, it renders the SNR worse, right? The other problem here is they're very unpredictable. I can't imagine the number of times across a community you've added a surfactant and it made the sample worse. Unfortunately, a lot of those aren't documented, but nonetheless, I can imagine a lot of people have tried thousands upon thousands of different combinations and had, very poor outcomes. And so, because of this, it tends to be very laborious and time consuming on the screening and incredibly stochastic. And so, what my group wanted to do is kind of take the best of both worlds. How can we use next generation instrumentation and then revamp basically the idea of how we approach the stochasticity with small molecules? And so we've actually had great success with the SPT LabTech Chameleon. And so what we like about this is under traditional blot and plunge style freezing, where you apply 3 to 4 microliters of sample, you wick it away with blotting paper, and then over the course of, 8 to 10 seconds, you then allow it to wick, thin, and then you vitrify. With the chameleon or the spotted on for that matter, you take a self-wicking grid with nanowires. You spray the sample on there using a picoliter dispenser. There is effectively no blotting. The grids are self-wicking, and so that's what's used for thinning. And then you can vitrify as quickly as 54 milliseconds or as long as 1 second, depending on what you need. And so with this, you can tune the ice thickness. And so what we really like about this is you get a very characteristic, what's called an ice stripe on every grid prepared with the chameleon or the spotted on. All of this, unfortunately, is empty, but that's okay. You have great density of holes in each square. And then across thick, middle thickness, and thin specimens, you can basically evaluate how your sample behaves in thick, medium thick, and thin ice. You can look at the ice thickness based on the energy filter if you have one, or you can look at the confidence of the CTF fit to get an idea of what type of signal you have in each of those images. And then what we do typically is we'll collect a few images at each of these different thicknesses, and then we'll get an idea of how our particles are behaving. Do they like thick ice, thin ice? Are we getting multiple views? And then we can basically tailor our data collection based on these quick screenings. And so what we've done is we've gone from this style of screening where we spend 30 to 40 minutes on each grid, identifying which grid square we want to collect on. And on the Chameleon, we can triage a grid in less than 5 minutes based on just quick screening. And we can move through sample to sample to sample very quickly, knowing that our thin sections here, our medium thickness is here, and our thick is there. And we can basically tailor freezing conditions, data collection based on that type of outcome. And so, even though it's not a silver bullet, it has expedited our ability to move through samples and collect really high quality data. Now, what's also interesting here is that one of the specimens that we've been working on for several years now, I worked with one of my postdocs to put this into ice. We had a great sample, it was very well behaved, and no matter what he and I did, we always got images that looked like this. All the particles were basically moved to the periphery, they were overlapping, clumping, even though we had great density. Same exact specimen, we moved to the chameleon and we started to get multiple different views, much better particle distribution, but it still wasn't producing the best sample. You can see this in the 2Ds, where under the traditional blot and plunge, where I physically froze these, so it's not a factor of like my postdoc versus me, like I froze these specimens, so I can say that they weren't great. When we move to the chameleon, you can immediately see in the 2D class averages, you can start to see secondary structure features, different views, but the grids still weren't great. And so then we started looking into different additives. And when we moved into our surfactant cocktail, almost immediately the quality of the data improved significantly. We got multiple different views. And importantly, we recovered a dimeric species and not an equilibrium of monomer dimers and a big heterogeneous distribution. Now, what is this surfact, right? So what are we talking about when we said a surfactant cocktail? So what we thought about is we know that surfactants can help with air-water interface issues. We know that they alter the chemistry of the freezing process, and importantly, they typically mitigate any type of air-water interface damage your specimen may encounter. Of course, some surfactants will actually destroy your sample, so there is, that big caveat. We also know that different classes act through different mechanisms. We know that zwitterionic or even fluorinated act very differently. Fluorinated polymers tend to act as kind of a hydrophobic, non-hydrophobic type chemistry. And so there's also different behaviors expected with this. And then we also know that different combinations can either stabilize or fragile complexes and improve grid quality, or they can do the exact opposite, depending on how stable your complex is. But overall, the idea is that when you add a surfactant into your mixture before freezing, it'll preferentially interface with the AWI and prevent your molecule from basically bumping up against it and therefore being destabilized, forming these preferred orientations, or even becoming damaged, right? That's the idea. Now, across all of the different specimens and projects in my group, what we found is that every single time we encountered a pathological preferred orientation problem, we just started throwing different surfactants at the problem. So what we wanted to do is take a step back and go into the EMDB, find pretty much every paper that's been associated with an entry in the EMDB. We, at the time of this, which I believe was October or November of last year, we found over 11,000. We then went through those and curated only the papers that mentioned a surfactant in the methods that specifically mentioned air-water interface issues. All right, and so of those, we found 655. And so this work was a tour de force from three undergrads in my group. And so what they did is they first manually went through and took the method sections and curated these by hand. And then we trained an AI to further validate these to make sure that we hadn't missed anything and that we had a double layer of validation. What we then did is we broke these down into their different surfactant classes. We had non-ionic, which is by far the largest class. These comprise octoglucoside, NP40, LMNG, and FOM. We then had the zwitterionic class, which is dominated heavily by chapso or even chaps or phosphocholine 8. We then had the amphiphilic class, which was dominated almost exclusively by the amphipole A835. And then we had this combination class where we had a mixture of different surfactants. Now, one thing I want to do is I want to make a call to the community. I'm also at fault here, but I will say that I was surprised at how heavily under annotated a lot of the entries are in the EMDB. And so the reason I had to employ a team of three undergrads and an AI is because scraping this type of information from the EMDB and even manuscripts for that matter was very time consuming and laborious. And so I hope with this call that people can feel free to put as much information as you can so that way we can approach this with more of a design and less stochasticity, right? Now, the crystallography community has tons of examples on how they scrape the PDB to learn things about um, what's happened over the years, and they even have annotated how lysozyme can bias things. We need to do something like this for our community as well. Now, what we learned from this is that there are different classes, different outcomes, but also that in each of these cases, the percent of the CMC or the critical micelle concentration at which these were added to each individual sample varied by orders of magnitude. And so one of the problems with this is that, well, you have four different classes, you have combinations as well. You have, even with the non-ionic class, you have five different surfactants you could use. You have a wide variety of different percent of CMCs you could use. And so for someone going down this rabbit hole, where do you begin? right? Which surfactant do you choose? Which concentration do you choose? Where do you add it? When do you add it? And then honestly, let's say that, this was a scraping across all the years, right? And so what we also found is that a lot of these additives fall in and out of favor over the years, right? And so I can remember when MP40 was everyone's favorite additive, right? Now I think Chapso is one of the big favorites across the community. The Lander Lab just put out a paper where they use DM as one of their favorite additives. And so there is this, in and out of favor, as well as the different percent CMCs, the different combinations. So what we wanted to do is knowing that finding a working surfactant concentration is incredibly hard to perfect, right? The reason being is that anytime you start to add a surfactant, you change the hydrophobic nature of the foil hull, the ice thickness, all these different things. And predominantly what people observe is this phenotype where all your particles get more or less pushed to the edge. And so if you're looking top down, this is what you'll see. This is the center of the hole. All your particles are pushed to the edge where it's a little bit thicker. And so you get this protein squeezing, right? And so finding a concentration where you can flip views without pushing all your particles to the edge is something that you have to tailor, right? The other big downside here is that some of the surfactants that tend to work really well, like Chapso for that matter, also tends to bind proteins. And so in this example here, you can actually see Chapso helped flip the views of this molecule, but it also bound to the surface of the molecule. And so therefore you have to then worry about, even if you don't see it, what's the surfactant doing to the overall structure, dynamics, stuff like that. Especially the higher you get of the percent CMC, the more likely something like this is going to happen. Then the other thing that's really hard to perfect is the decreased particle density is a known byproduct, but it's very stochastic. And so what I mean by this is you take your sample, you freeze it, let's say 10 megs per mil, you get preferred orientation, but you had great particle density, right? You can see something like this here, right? Then what you do is you add chaps or chapso or a surfactant, you get different views, but your particles are pretty much gone, right? Where did all your particles go? This is a known byproduct. And so how can we reconcile what's happening when you add just a single small molecule surfactant? And so what we sought to do was basically create a surfactant mixture that solves as much of the air-water interface problem as we possibly can while minimizing the individual downsides of in these surfactants on their own. And so a lot of this came from my background in X-ray crystallography when I was a grad student. And so the idea here is why can't we fix this? Why hasn't there been a solved problem for the air-water interface? And what can we do to fix this? So we think that this isn't solved because there's so much unpredictability and it's underreported which ones didn't work, right? So there's tons of artifacts, there's lots of sample instability, and you only really hear about this at conferences and, over lunch or something like that. More importantly, we don't really truly understand how a lot of these surfactants are working alone or in combination. We don't really understand how they're affecting the interfaces or even particle behaviors. We just know that they work or don't work. And so, at least with X-ray crystallography, the analogy here is when you have a beautiful crystal, you have to then add a cryoprotectant to vitrify it, to freeze it, so that way when you put it in the X-ray beam, you don't get tons of damage. And so what's nice about this is you can take crystals and screen cryoprotectants and your readout is really quick. You either get great diffraction or if it's a bad cryoprotectant, you get terrible diffraction, right? You can do this very quickly and robustly screen, but what we wanted to do is eliminate that stochasticity, right? And so there was a really great study by Elspeth Scarman's group back in the day where instead of taking a single cryoprotectant for their crystals like glycerol or ethylene glycol or something, they created mixtures called cryomixes where they varied the ratios of each of these known different cryoprotectants. But rather than having a single high concentration of one, they had low concentrations of all of them. And what they observed as across the board, you got big improvements in the number of targets that worked well with it. You had decreases in the number of ill side effects from a single cryoprotectant, and your screening became limited because you didn't have to go through each individual cryoprotectant at high concentrations. Now, what we did is we went back through our data curation of the EMDB, our scraping, and we decided that we would use Chapso, which is a Zwitter ionic detergent, FOM, which is an amphiphilic fluorinated surfactant. We used AA35, which is its own weird amphiphilic polymer, and also Breeze 35, which is a non-ionic surfactant. And so the idea is every single one of these are going to be much lower than tenfold below their CMC, which is lower than what you would typically use by themselves on their own. And then importantly, every single one of these were either shown directly to either decrease air-water interface issues. Importantly, Chapso, I think a lot of people have used Chapso. FOM has been used to stabilize fragile protein complexes. We also know A35 has been used in many cases. And then Breeze 35 in most cases can reduce surface tension during freezing and also decrease aggregation, right? And so every one of these has on their own a potential benefit for a sample. But then we mix them at much lower concentrations so that way you don't have the ill effects of a single surfactant decreasing stability of your sample. All right, so where did we start? We started with hemagglutinin trimer because pretty much everyone with preferred orientation starts with this. And so real quickly, if you look top down, which is this view, you have a threefold symmetry axis, and this is the dominant view of HA trimer when it is stuck at the air-water interface. And then this other side view where you can see the head and the stem, which represented here, this is lost typically when you have preferred orientation. And so what you see is because you're dominated by these top-down views, you lose the Z thickness of the specimen. You get the streaking of your molecule. You get overfitting as a result of biased views. And then when you can reconstruct the entire object, this is what it looks like, right? Now, the real telltale from having missing views is when you have missing cones or missing views in Fourier space, they manifest in real space as loss of contiguous density and stretching, right? And so even if you have a high resolution structure, if you're missing information in Fourier space, you're going to get these artifacts. Now, being at UC San Diego and also having come from Scripps Research from my postdoc, we went to our friends at the Ward Lab, specifically Dr. Julianne Hahn at the Ward Group, and carefully asked them for some of their pristine hemagglutinin trimer. And so what we did is we froze this using what's called, traditional EM sample preparation. This was frozen on the chameleon. You can see here you have great contrast, lots of particles, great particle density. But if you're looking closely, you can already see that a lot of these have the threefold dots or the preferred view of HA trimer. When we froze the same specimen now with our Surfact cocktail, you can see that first the particle density is lower, right? That was the immediate thing that we saw. That was kind of expected. But then you can also very clearly see side views of our HA trimer. When you look at this via 2Ds, right, on traditional, you see the top-down view is dominated in our 2Ds, whereas with Surfact and the Chameleon, we're dominated now by side views and tilted views. So immediately we can see we're recovering those views and we still have our top-down. If we look at elevation plots, we can see that in fact, this sample was dominated by two different views, top and down, whereas now we've almost filled in the entirety of Fourier space. If you look at the 3D reconstructions with the traditional, you see the pathological phenotype of preferred views, whereas here we can now reconstruct the entire object in its totality. Resolution wise, we were able to get a 3 angstrom resolution from these preferred views. But if you look here, this resolution metric called CFAR, which tells you how limited your viewing distribution is, 0 being absolutely poor, 1 being perfect, it was 0.02, which means you're missing tons of information in Fourier space and limited views. But when we add surfact, we now have a CFAR of 0.93, again, one being perfect, which means we're about as high as we can get without being, apoferritin. Now, hemagglutinin trimer worked great. We then moved to another specimen that doesn't have as preferred views, but experiences sample denaturation. So when I was a postdoc, I worked with a very talented grad student, Mingyu Wu, in Gabe Lander's lab. And we were looking at this aldolase, which is a 140 kilodalton homotetramer, to push limits of cryo-EM and sample imaging. And at the time, this was almost 10 years ago now, we had to enforce D2 symmetry to reconstruct this object, right? Because at the time, when you were working with smaller stuff, you had issues reconstructing the 3D object unless you enforce symmetry. Now, the downside of this is that when you enforce D2 symmetry, you get a beautiful reconstruction of the object. But now with newer algorithms, we can reconstruct this using C1 symmetry. And what we noticed was that there was almost always one protomer of aldolase that was always weaker in some capacity. And so then what we noticed was that if you look at this specimen, you get great particle density, beautiful 2D class averages, but there's always one protomer that's missing or completely lost. And so we can see here that even though we have a fairly decent CFAR, what's happening is that we are losing a portion of this sample that's being destabilized at the air-water interface, and it's biasing our viewing distribution that can only be recovered through symmetry, right? Even though it's a 2.4 angstrom structure. Now, when we add surfact, again, you see the concentration of your sample drop, but you still get beautiful 2D class averages. And with C1 symmetry, you now recover the entirety of every single protomer. And if you look at the viewing distribution, you now can see in our elevation plot, we have almost all the views recovered. So we've eliminated the interactions with the air-water interface, recovered the integrity of the molecule, and now we can reconstruct it without having to enforce symmetry. Now, what we also notice is that this is titratable. And so when we move from 0x through 0.25, zero point 0.5, or 1x of our formulated working concentration, we can see that the resolution ranges a little bit from 2.4 to 2.5, but more or less the integrity of this broken protomer changes as a result of the working concentration. So the higher the concentration you use, the more of this intact protomer you recover. So it's titratable. What you can also see is that you go from a lower CFAR to a much higher CFAR almost immediately upon addition. Higher concentrations give you a much better viewing distribution. And so here is more or less what we designate as 1x. This is what you would start with probably to basically eliminate the air-water interface issues and have a great working concentration. Now, we use a chameleon for this, right? But I'll let you also know that it worked for the VitraBot as well, for all you VitraBlotters out there. So again, here's 0x on the VitraBot, 1x with our surfact. You can see the difference in the densities between the different reconstructions. One's at 2.15, one's at 2.1, both great. And it also works on a manually operated plunger, so you can use it on pretty much any freezing modality. And then you can see here the differences in the elevation plots, right? So it works great. Now, one thing I do want to highlight, which is we found very interesting, is coming from this 0.25x. And so what we noticed in our data processing is that moving through 2D classification into 3D, we can basically binarize our sample into one of two different groups: fully intact with an intact homotetramer, or again, one with that broken protomer phenotype. All right, so it means that it fixed in some cases, but not completely. How do we reconcile this? And so what we did is we turned to the Grosjean group as Scripps Research, who are experts in cryo-ET, and we took tomograms with them of our different aldolase samples. And so what we see is in this tomogram of our 12 mg per mil aldolase with our 0.25x surfact, we have a top bottom air water interface, and then we have a middle region here. And so through subtomogram averaging, we can split them out. And we see at the top and at the bottom air water interfaces, we have the broken protomer. and they're oriented 180 degrees apart because we have top oriented or bottom oriented, which explains why we're losing that protomer at the air-water interface. And then if we specifically reconstruct only those found in the middle, they're now perfectly intact. We have no loss of that protomer. So this was great to see that all of our good intact particles are coming from those at the center that have been prevented from binding to the air-water interface. Now, what was also really interesting is because we have the volume of this tomogram and we have coordinates, we can basically now estimate the particle density in this tomogram. And so what we saw is of our 12 mg per mil aldolase that was frozen, at the air-water interfaces, it's been concentrated almost threefold, specifically at the air-water interface, while in the middle, it's much closer to the concentration that we originally froze at. And so what we now think is that these super concentrated particles at the air-water interface are increasing the apparent particle density you have. And when you add a surfactant that breaks that interface, you're now no longer super concentrating and you're getting much closer to the actual working concentration you had before you froze. And to give you an idea, is this is what a tomogram of 12 mg per mil aldolase looks like with 1x surfact, right? And so you can see the marked difference in how they're distributed in Z across these different ice. Um, Now, so what do we know? We know that this surfactant cocktail in its current formulation improves the viewing distribution of multiple different samples we tested. And importantly, it preserves the fragile domains that get denatured and unfortunately get lost at the air-water interface. What we also know is that it preferentially wants to be mixed at a 1-to-1 ratio. So you have your sample at 2x, you have your surfact at 2x. And the reason for this is it has minimal sample disturbance versus adding a very concentrated working stock and then diluting it in your sample. And so that we've seen works best for this. What's also nice is this formulation can be stored indefinitely, and you can also now work with dropouts and different ratios of the mixture tailored to your specific specimen. And we also know that it can be applicable to almost any soluble protein. Unfortunately, yet we have not tailored it for integral membrane proteins, I think for obvious reasons. But we have started working on IMPs that are solubilized in nanodiscs because we then don't have to worry about breaking up micelles that some of these surfactants will do. And so with that, we're hoping that, people will continue to use it and give us feedback because as we tailor this for multiple formulations, we're looking for what the community needs and wants and get their feedback. And so now with the last, 4 or 5 minutes real quick, I want to segue into one other thing that we've done in dealing with both the air-water interface as well as oxygen. And so I think Christina is going to be very happy to see this, having also worked on oxygen sensitive proteins in her previous life, like I did. And so one of the things that we have to think about is that for any oxygen sensitive protein, once you isolate it, you have to put it immediately into an anaerobic glove bag. And you have to keep it away from oxygen during the entire process of handling and even vitrification for that matter. Now, once you have the sample preparation and isolation in a glove bag, these are anaerobic conditions. You can tailor these conditions specifically for that anaerobic environment. But once you then remove it from the anaerobic environment, it's a race against time because oxygen damages stuff. Now, there are opportunities to put specimen plungers in a glove bag, but not everyone can do that. And so what we wanted to do is basically say, well, if you have access to an anaerobic chamber, and you have access to a chameleon or spotted on, can you still vitrify your sample under anoxic conditions? And so what we then do is you take your specimen, you layer it under anaerobic Al's oil, which is a mixture of paraffin and silicon oil, in the chameleon cup. And so what this oil does is it doesn't prevent air from entering the specimen, but it slows down the diffusion of air long enough to where you can basically handle the specimen, get it into the chameleon, and then keep it under anaerobic conditions. You seal it under a reactive vial with a septa under anaerobic environment until you need to pop it open and put in the chameleon. which works great. And then we have an oxygen scavenger in the system to prevent any leakage. It's then transferred into the chameleon. It's maintained anaerobic with the oxygen scavenger. And then we basically squirt it onto an EM grid. You freeze it within 100 milliseconds, and you can recover samples without oxygen damage. Now, the paper here is published, so I'll let people look into here for the details, but we can also tune the parameters of plunge times for ice thickness and other things depending on sample requirements, and it works phenomenally for a lot of very difficult specimens. Now, the last thing I want to touch on is the algorithmic interface because I still think there's a lot of avenues here, and we have an interesting approach that I want to get feedback on from the community. So one of the things that we noticed is that in 3D classification, if you get these bad particles into your 3D classification, they're really hard to get out. And so what we did is we trained an AI called Antidote, where we took these different data sets and we specifically poisoned them with bad data. And so now we have labels of good data and bad data. We can monitor their distributions through 3D classification, and we train the AI to look at those behaviors. And so it's not looking at the particle images, but it's looking at the behaviors. And then through this neural network, it gives a ranking of percent true or percent false on a per class basis. And then what you can do is instead of picking each class on their own, you pick the good particles regardless of what class they came from. And so what we see is let's take aldolase, for example. If you classify an aldolase data set that's been poisoned into 5 classes, you get a distribution like this, where you have across the iterations, this is the percent true, this is the percent false, and it varies depending on class and depending on iteration. And so what we can do with this neural network is it picks out and ranks all the particles, and then you can pull them out to reconstruct them. And so for hemoglobin, if you take an uncurated particle stack, run it through 3D classification, you get rankings on a per class basis. You can then pull out only the true particles and reconstruct them. And you go from something like this to something like this without having to do heavily involved 3D classification. And so the benefit of this is that it's particle shape and size agnostic. It doesn't care because it's never seen the actual images. You can run inference on less than a minute on your data. It's already available on GitHub, and importantly, it directly integrates within Relion 5.0. And so across that, as we think about how we deal with these different interfaces, you may have to apply all, but we're hoping that between Surfact and some of the algorithmic stuff, you can improve your sample. And so, of course, I didn't do this in a vacuum. I have an absolutely amazing team. This Surfact paper had pretty much everybody in my group contribute, which was fantastic. I also have great collaborators, both at UCSD and beyond. I have also great funding resources and want to thank you all for your time and welcome any questions you may have.
Thank you. Okay, a question just showed up. Great talk. Thank you. Can you please show the surfact composition again? And the question, do you think surfact helps with reducing the protein dynamics?
That's a great question. We don't know if well, I would say that the mixture was designed specifically so that you hopefully don't have enough working concentration to bind to the exterior of the sample to potentially influence dynamics, but rather each one of these have different kinetic preferences at the air-water interface. And so as you're having that wicking shearing, you're having a constant replacement of either FOM, CHAPSO, or something at the air-water interface and preventing your sample from interacting with it. Um, Caveat there is that we do know of at least one specimen where specifically the amphipole has destabilized it. And then we also know that there are other examples of chapso stabilizing proteins, but they bind to the exterior.
Okay, another question. Are you going to come up with commercial screens available, like the X-ray crystallography screening
Great question.
mixtures?
That's a work in progress. I'm waiting on tech transfer at between UCSD, but I have been approached by several vendors to market this. And what we're thinking is that we're going to market basically a combination of six, where we have either dropouts or different working concentrations of components. So that way you can basically screen. And so we're working right now on developing the dropouts in different working concentrations based both on different physical chemical properties, but also based on what the literature has shown us.
Okay. Would it be possible, another question, would it be possible to overcome the problem of loss of particle density following this surfactant addition by increasing the sample concentration, just jack, jacking up the sample concentration?
That's what we have found to be most common in some cases. Um, and so usually we start with a 2x and then you dilute it to what your 1x would be. And then if that's too dilute at the particle level in the grid, then you can just simply double the particle and it scales much better than what we've
Mhm.
seen previously. I would say that we have not at this stage strived to increase particle density for any of these samples based on what we've shown. That's what we showed in these images is what went into the reconstructions. And at those particle densities, with the conditions that we have in the paper, most of the reconstructions went into the low 2 angstrom range. And so you don't really need to get super ultra high density for these to work, but it does help for throughput.
You don't need lots of particles, you just need good particles.
Yeah, and so one of the dropouts that we did, we collected 200 movies of our HH trimer and had 8,000 particles, and it went to 2.5 angstroms.
Mhm.
And so you don't need a ton of particles, you just need good viewing distribution and high quality particles.
Mhm. This is a good question. Do you expect the surfactants to saturate the air-water interface at their respective concentrations in surfact?
This is what we're thinking is that if it's not completely saturating the air-water interface, it's doing so to such an extent that you're not allowing the particles to bounce on and off the numerous times that's anticipated based on modeling. Because what we see, I mean, the only problem we have, and I can show this real quick, is if you look at this tomogram, you
Mhm.
can clearly see right here, there's a boundary here. We don't know if that's the air-water interface boundary purely or if it's contaminated to what extent with the surfactants. So we don't know if that surfactant layer is 5 angstroms, 50 angstroms, or whatever it is, but we do know that at least across this Z, the particles are evenly distributed, and
Mhm.
that works for us.
Okay.
If I can interrupt between
No, go ahead.
questions for a
Yes.
second, for anyone who has to leave, as we're at the hour, we'll if Mark can stay another couple minutes, we'll get to these questions and we'll keep recording.
Yeah.
So if you have to leave and we didn't get to your question, come find the recording. And if you have to head out, we hope you join us again next time. Good luck with your cryo-EM. As you see, it's hard work for everyone, but we hope all of these tips help. And we hope you all go try out this antidote and give Mark some feedback because I think he's genuine when he says he's looking for community feedback on that.
Thank you.
And yeah, we'll keep going with a few more questions.
Okay, sure. A, a naive question, but are these surfacts only for globular particles, or can they be used with microtubules, presumably fibers, or helical proteins, for instance?
So we have not tested them on anything as long as microtubules. Microtubules are interesting, and I think also actin is that when they have the shear stress during blotting, they tend to bundle. But we do know from one sample that was filamentous that it worked just fine. And the caveat there is that the filament lengths of this sample varied substantially from like maybe a few hundred angstroms to thousands of angstroms. But we didn't get bias viewing or anything crazy, at least with that filamentous sample.
Mhm. Sort of, I mean, helical objects, obviously, they would present different views towards the air-water interface anyway. So, and with the helical averaging you have to do, you wouldn't really know which side was up and which side was down, in a helix because they're
We
all there.
We have had one group reach out to us who are doing filamentous MOFs, these metallic organic frameworks,
Oh,
where they don't have very large symmetry across the filaments, and so they do need help kicking the views around. But for
mm,
anything where you have, you know, a higher lattice geometry, then you shouldn't have to worry about it as much. Yeah.
right. Okay. Can you tell us what your experience with fluorphospholine 8? We have some previous good experience with it, and they were surprised that it was not included in the mix.
We have not used that. We've also talked to a few people who had really good luck with like octoglucoside and phospholinate. And so we are exploring doing dropouts where we add one of those in replacement of other ones that have slightly similar chemical properties. And so, what we're hoping for is this current formulation is not going to work for every sample, but we're hoping that across the different formulations and with community feedback, we can get something that does work.
Okay, I think you mentioned this in passing. Do you have any initial thoughts on surfactants with membrane proteins in nanodiscs, and that they've tried with this but haven't had success with the ones we've tried? So the nanodisc versus micelle uh, preservation of IMPs.
I would say that that is by far the first target that we're pursuing for integral membrane proteins for the reasons you outlined. I think there is a limitation on at what concentrations we can use because eventually I think you will start to rip off the belt protein or something. The other caveat there is the people that we've approached to use their problematic IMPs and nanodiscs, they're also using antibodies to help kick views. And so um, we have to be careful about not kicking off the antibodies that they need for reconstructing the object and breaking the pseudosymmetry. And so that's kind of where we're at right now.
Okay, question. Is there a way to know from the images if there's denaturation at airborne interface, or if there's some other issue? That is, look at looking at the images and presumably the reconstructions you could get from them. Um, that's certainly a good way to see
Yeah.
if there's if there's a problem.
Yeah, I think the biggest issue, I mean, even autolace is a great example. Like I've been looking at
Mhm.
images of autolace for over a decade now, right? And it doesn't present as obviously denatured because you get different views where you
Yeah,
can see it's
yeah.
obviously intact. But the problem is that usually what's denatured or what's destabilized is looking dead at you through Z. And so it's then also you're being projected through the rest of the molecule. And so you don't typically see it until you start to reconstruct it fully in 3D. And so in that case, it is sometimes
Could be.
hard unless you have something with like a big domain that's missing or you see complex start to fall apart.
And another thing is that this denatured object on top, or even mixed in with your protein, just actually affects the orientation search that you're doing anyway. So the pose is not the right pose for the rest of it. So it messes up it messes up everything because of its presence in one place. So yeah, I mean, yeah,
Yeah, and
and
so
so
real quick, so autolace is a good example to where if you take this, I'll show right here. So if you take these particles here and then you provide it with a D2 reconstruction that hasn't been low passed enough, this domain here will start to average across the different protomers.
Mhm.
But if you start completely asymmetric, no symmetry imposed, they all group to one protomer. So
Mhm.
if you start to enforce symmetry too early, this will be averaged across everything, and you'll think everyone has a weakened protomer, when in fact it's just one that's being misaveraged. And so
Mhm.
not enforcing symmetry too early is a great way to figure out if and how much of your sample is destabilized.
Mhm. Let's see. Oh, presumably this is also a question about membrane proteins. Have you tried surfactant cocktail with membrane proteins solubilized in my cells? So presumably
We have
that's
not.
something that doesn't work too well.
We have not, and people that we've asked to try it, they've told us no, so it's fine.
Okay. Here's the contrary view. Have you observed conditions under which surfactants don't provide a benefit at all?
Yes, we have. There's been several actually. We have one example where the current formulation actually breaks apart the complex,
Mhm.
and then when they drop out A835, it works okay. We have another example with hemoglobin where we added it and it didn't change the viewing distribution at all, but it also didn't destroy the sample. And so it was more or less just there adding scattering to hemoglobin. Um, and we have another example where it seemed to help a little bit, but it wasn't as a binary type improvement from HA to what we saw with Surfact.
And here's a question that mixes with a question that I would have. Um, how how can you tell whether your preferred orientation is not the preferred orientation of the sample preparation, but it's the preferred orientation of the particles you picked?
Oh, that's a great question. I would say
You didn't
most
look for them.
Most of the time, we don't even look for them really, right? I would say a big part of this too is like I think most people really don't care. There's like it's broken or not. But I think what's interesting with the aldolase example is the particles in the homogram that distribute in the middle are completely intact. And so
Mhm.
that means that the sample was intact and it still was vitrified intact. Now, whether or not those never encountered the air-water interface or just didn't encounter it enough to be destabilized, that we don't know because we
Mhm.
only have like predictions of how many times they would bounce on and off. But, you know, if they're recovered on the other side, then, that's at least something.
Mhm. Well, I think this question was okay, you see preferred orientation in your sample is because those particles that were in that orientation were the only particles you recognized as particles and picked. The other ones are there, but
Oh,
you didn't choose you didn't blob pick those.
right.
You
There's
all picked one.
Yeah, to that point, there's a really good tutorial on the CryoSpark webpage about hemagglutinin, about how for that type of specimen with different orthogonal views, where you have a smaller diameter top and a bigger diameter long view, depending on how you pick the particles, it biases the viewing distribution and how sometimes you need to actually prune out the overpopulated view to reconstruct it. And so there's a good example of that. And I think also there is a Dynactin paper from like 2016 from the Andrew Carter's group where they saw the same thing, where they had to basically tune the viewing distribution to reconstruct. Otherwise, it was quote unquote pathologically preferred.
Okay. Yeah. Is there a standard preferred? Okay. This this is a question that you probably just answered. Is there a standard preferred orientation workflow fixed after 2D classes you'd recommend on CryoSpark? So again, it's image processing rather than sample prep.
Exactly. And I think this is the problem is it's so subjective, right? You need to be able to look at your 2D classes and figure out is it you're underpicked? Is it a result of you've so overpicked the dominant view that you have now class collapse, where your underpopulated views have collapsed into your overpopulated views? We see this with the 20S proteasome a lot. Or is it a combination thereof, right? And so I think, you have to kind of take each one on its own.
Okay, and a clarification on a question that I may have not asked in the proper way. Um, Sorry, my question regarding denaturation of the air-water interface was, how do we know if the low resolution of a particular domain is because of denaturation at the air-water interface or the dynamic nature of the protein itself? And
Oh, I see. So basically, if at low resolution you can see the subdomain, but then at high resolution it's lost. That's a combination of things in my mind. I think one, it's the dynamics of that region does not allow you to reconstruct it to high res. And so whether or not that's inherent dynamics, whether or not it's dynamics that's exacerbated because it's interacting with the air-water interface,
Mhm.
that we can't purely uncouple. But at least at the final high-res reconstruction, usually because that region's lower resolution, it's being sharpened to the same extent as the rest of the reconstruction. And so that's why that density is weaker or lost. And in that case, usually local filtering can recover it. And then once you have those insights, the biology is going to dictate whether that region's dynamic because the molecule is expected to be dynamic there, or if it's just a result of, humans handling it.
Mhm. And I think you kind of answered the question. That really the only way you noticed that is because you did the tomogram and you saw which end of the which part of the protein was up or down, and that was the part that was denatured. So all other things being equal, it was because it was in at the air water interface because that's the way it was pointed
Right.
when you. But you don't get that usually except in tomograms. So it's hard to do it any other way. This is interesting. Have you tried the surfactant cocktail with protein nucleic acid complexes? Let's throw in some DNA and RNA.
Yeah.
What does that
We
do?
have a couple groups that have tried them. One with RNA polymerase, and it worked really
Mhm,
well.
mhm,
Um, I don't have the data off with me right now, but anecdotally, they told me that it worked quite well. And we've have another group that used it, and they said that it didn't work so great. I think it was on a tRNA complex, but I think those are also quite fickle. So
mhm,
yes and no, I would say.
mhm. Okay. Looks like that's the last, and we have everyone thanking you for a great discussion, and
If,
this is great.
if I can take my host privilege to ask one last question.
Yeah.
So your
Go ahead.
recommendation to do a 2x and not a 10x stock, how strong is that recommendation? And what's your observation of like what goes wrong when you add in a more concentrated stock?
That's a great question. So we have one group that did use a much higher working concentration to dilute, and they had a very poor outcome until they mixed it at 1 to 1 like we recommended. And so we haven't proved this. I'll be fully transparent here, but our thinking is that when you have a 10x working stock, you're approaching the CMC of a lot of these. And because of their different properties, the breakdown from that micellar population back into the free components can potentially be too slow. And so at that point, you're not really actually having a nice homogeneous distribution of the free surfactant molecules that you need at the air-water interface. Whereas you may have more of them distributed still in the micellar population. Um, and we think that leads to a poorer outcome than keeping it low. And so what we prefer to do is mix it at our 2x working concentration, and then, we can leave it for a little bit as long as it doesn't oxidize or anything. And so that way everything's fully equilibrated. We don't have a big micelle population. We have basically every monomeric surfactant to hit the air-water interface. The other thing that we have seen, at least for one example of ours, is when we add the higher working concentration, we can recover a population that's intact, but the population that's still broken is much larger than what it was when we have the one-to-one mixing. And so it's not that it's a complete like binary yes or no, it works, but we have much better outcomes when you mix it carefully one-to-one.
Awesome. Thank you. Yeah, thanks so much for sticking around to get to all of our questions. This was a lot of useful advice. And I think I can speak on behalf of everyone and say this was extremely helpful. So thank you, Mark.
I'm glad everyone could attend. And thanks for the invitation.
Thanks. Thanks again.